Hi everyone, welcome back to another video in the series of Understanding Apache Parquet. In previous videos, we've taken a look at high-level overview of how Apache Parquet works and how we can create Parquet files. However, in this video, it's more of a deep dive, if you will. We'll take a look at some of the internals, inner workings, if you will, of how Apache Parquet is structured. And basically, in the video, we'll chunk it into two parts. The first part, we'll take a look at some of the key concepts that we have to be aware of before we then dive into a demo. Again, in this video, I'll be spending much of the time will be spent on the demo itself. We'll take a look at a tool which will help us introspect and look at the internals of the Parquet file format. So that's really the objective of this video. So first off, let's dive in and understand some of the key concepts. But again, it's helpful before we actually get into some of the more advanced concepts. Just a quick refresher, if you will, on how Parquet works. So again, I've covered this in fair bit of detail in a previous video, which you'll find in the video description below. But just to jog your memory, if you will, in terms of what we have covered at a high level. So imagine, if you will, that you had a table which contains three columns, A, B, and C. As you can imagine, these are kind of like a logical view of how that table will store the data. However, from a physical representation standpoint, more traditional ways of storing data typically relied on a row-oriented layout. So essentially what would happen is you have each row followed by the adjacent row, if you will. So you have for the three columns A, B, and C, you have the first row A1, B1, C1. So we'll take that and store that first, and then take the second row and store that or append that, and on and on and on. So that's how traditional row-oriented systems used to work. Pretty much a lot of the backend systems prior to columnar storage formats typically stored it in that fashion. However, columnar oriented stores such as Parquet, as the name suggests, stores data of all the columns first, and then following columns are stored in order. So in this particular example, you can see that instead of storing every column of every row appended by one another, we first store the columns first, or the same column data first. So here we are storing all the values of column A first, and then we store the values of column B, and then finally store values of column C. So this is essentially how Parquet works. So it's a columnar storage. So that's kind of like a quick recap of columnar storage. Again, if you want to know more about the Parquet format itself and a columnar nature, take a look at my previous videos. However, the intent of providing this context is for us to get into the real meat of our discussion for this video, which is the internals of how Apache Parquet works. Now, think about it for a minute. If you think about a columnar layout such as what we have just discussed here, have you ever wondered how the actual physical file is created? So imagine, if you will, that again, if you had all of these data, all the columns laid out in this order. Let's say it's not just 5 rows of data. Let's say you had 1,000,000 or even 1 billion rows of data. How would that actually transpire into the actual physical layout within Parquet? So think of it as what do you think for a sec? Is it a case where we would end up with just one file, one huge ginormous file, or would we end up with multiple files? Now, obviously, it's unlikely to be a single file, and if you had your doubts here, obviously right, that it's not a single file that gets generated in vast majority of the cases. You will end up with lots of files, because if you had a single file, that'll be a terrible waste of memory and resources and would hinder parallel write performances. So if you have tried creating Parquet file using, say, for example, Spark or even Hive, you would have, if you have looked under the hood into the HDFS folder or the underlying store, you would have noticed that it's created multiple Parquet files. So there's a reason why there are multiple files generated, and part of this video is to explore why it generates these many files. So that's at a high level the concept behind a columnar store. But then going slightly deeper into the actual Apache Parquet format itself, um, there are a couple of key concepts that we need to get familiar with. So imagine, if you will, that this is a single Parquet file. So again, we discussed in the previous slide that you, for a given table, you will end up most likely having many number of Parquet files, and there are different parameters and settings and dependencies that would result in n number of these files being generated as opposed to a single Parquet file. However, within a given Parquet file, there are three parameters or three concepts that we need to understand. So the first thing we need to understand is what is a block size. Now, a block size, when referred to Parquet, is different than the block size that we refer to in a system such as HDFS. Note the two, there are certain dependencies, but they're not the same. And in vast majority of cases, you will want to keep your block size for Parquet a multiple, if you will, of the HDFS block size. So again, the default for Apache Parquet is 128 MB for the Parquet block size, but again, it would depend on your distribution and obviously the version and of Parquet, as well as the underlying subsystem you're using to create and read these Parquet files. So again, that's essentially the block size, and the block size basically dictates how large a given file size can be. Now, within the block size itself, we have a concept called a row group. So many a times you'll find in online forums this idea of column chunking, and that's basically what's inside of a row group. So within a row group, you can see that we have different columns. So if in a previous example, you may remember that we had a logical table that had columns A, B, and C. So as an example, so you can see in row group 0 in this particular case, we have column A followed by column B. So effectively within a row group, it'll contain multiple columns. So again, you can set the size of the row group. It's a parameter that can be configured. Again, I forgot to mention about the block size itself, but if you wanted to tune the block size, there's a parameter or a settings that's parquet.block.size that can be used to change your block size. Similarly, you can optimize or potentially change the configuration for your row group. So again, within a row group, as I mentioned before, you have multiple columns that get stored. And finally, within a row group, as you can see, you have different constructs, what's referred to as a page. And it's actually the page which is the lowest level, which actually stores the details of the data itself. So that kind of gives you an idea in terms of the underlying structure of a Parquet file. Now, I've only gone through this at a very high level, haven't gone through it in a lot of detail, which again I'll cover as we step through the demo. But a couple of things you'll want to keep in mind, apart from the heavy terminologies that we have used and the theory that we have discussed. Keep in mind that there's a lot of performance driven parameters here that we have just discussed. So if you think about it, the parameters such as the size of the row group and the block size dictates the overall performance of your system. And there's never ever a right answer or a wrong answer or a universal answer in terms of what size you need to set. Again, there's a dependency on the shape or the structure of your data and the size of your data. But typically, think of it as a rule of thumb, like if you set higher block size, higher row group size and block size, it improves. So the higher value that you set, it improves your overall read performance, but it can consume a lot more memory when it comes to write operations. And also think of it as from a memory standpoint, a way to calculate memory would be in terms of the Parquet usage would be to multiply the row group size, that's this one here, against the total number of open files, and you get a rough idea in terms of how much memory is required to be consumed when you're reading your data set. So again, these are some guidelines, if you will, when working with Parquet. Again, in vast majority of cases, you may not need to go down that to that level, but it's always helpful to understand how Parquet itself works. Which brings us finally to the demo itself. So in the demo, I'll cover a lot of these concepts in more details. So let me switch over to the demo. Purposes of the demo, I've already created a sample data set in advance, and I'm just walking you through with what's there in the sample data set before we actually jump in and see what's there in the Parquet file. So I've taken sample public data set, which was originally in CSV, and I've converted that into a Parquet format. If you've not or rather, if you're not familiar with how you can do that, take a look at one of my previous videos. You'll find the link in the description below how you can create your own Parquet files. I'm not going through how you can create the file in this video, but just giving you an idea that this is what the Parquet file basically contains. So I'm using the data frame write operation. So this is what the Parquet file will contain. You'll notice that it contains a couple of different columns. Here's a snapshot of the data. The Parquet data itself has around 985 rows, and essentially this is the schema of the Parquet file. So what I've done again is just taken the CSV data and I've used infer schema and again use the data frame capability to write to a Parquet file. But essentially that's what the Parquet file contains. And looking at the Parquet file itself, let me actually switch over to this pane here and show you where the Parquet file itself is stored. Now the data that you saw here is effectively stored in HDFS, and here you can see that when I've used Spark to create the file, it's created in this particular instance one Parquet file. Again, when you play around with Parquet with small data sets, and depending on your cluster size and block size and the parallelism that you've selected as defaults, you may get more files, but in my case there's just one Parquet file here. So let's actually take a look at what's actually in this Parquet file. Now the tool that I'm going to use is Parquet. It's called Parquet-tool. So chances are in your Hadoop distribution you may already have Parquet tools pre-installed. If you don't already have Parquet tools pre-installed, you can actually go ahead and download it from GitHub and play around with it. Keep in mind that Parquet tool, while it's available within your Hadoop cluster, you can run it outside of your Hadoop cluster as well. So you can just point it to a Parquet file. However, in context of what I'm going to show you, since I've already got the Parquet file in an HDFS folder, I'm going to run it directly. If not, what you can do is you can copy this file from Hadoop and point it to, copy it to your local folder, local hard disk, and then use Parquet tools off of your local hard disk. So again, I'm just going to directly use it from HDFS. So let me just copy over the full path, copy the couple of different commands that we can run on Parquet tools. So the first command I'm going to run is schema, and since we are pointing it to HDFS, even before I do that, I need to know what the computer name is. Host name. Okay, so Parquet tools, schema, DFS. Let me just leave a gap there, paste the URI, and I'm just gonna copy this All right, so now we have the full URI. Keep in mind again that depending on your environment, the URI, particularly the host name, might vary. Again, it depends whether you've got Kerberos enabled and how your cluster is set up. So if you're having difficulty in putting together the URI, again, simplest step might be just to copy this file over to your local directory and just point it to your local hard disk. All right, so the first command we are going to look at is to take a look at the schema. So here you can see that's the underlying schema that Parquet is detected, and side by side I'm keeping the schema here on the left hand side is how Spark sees the schema. So again, you'll notice that the structure is maintained. Don't be overly concerned about the fact that this was a string and here's a binary. It's again a representation within Parquet. But essentially what you can see is this is the data set that we had from Spark, and when you can view the data set in Parquet using Parquet-tool. So that's the schema. The next command we'll take a look at is instead of looking at schema, let's actually take a look at a snapshot of the data itself. So we're going to run the next command, that's head. And head basically gives you a peek, if you will, into the underlying data that's stored in Parquet. So here you can see that each row is being listed out here. So maybe let's just go ahead and look at this data set, kind of like compare it side by side. So the first row, let's scroll up a bit. So the first row you can see the address 3562, that's this row here. So essentially the first row here, so you can actually see that's listed here, followed by the second row, third row. Again, it gives you an idea of the data itself that's stored in Parquet. So it's actually, let's run one other command and I'll kind of go back to a visual. Let's look at the next command, that's meta. Meta I found to be the most useful in inspecting the contents of a Parquet file. Let me just clear that. Let's run the same as. So now it's inspecting the Parquet file, and in this output, maybe I'll just explain a few of the things. So here you can see the version of the Parquet file and which particular version it was created by. You can see some additional pieces of information. Since I've created the file, the Parquet file using Spark, it adds a bunch of additional descriptors here. So for example, if you created the Parquet file using, say, Hive, you may not see some of this information. Again, this itself isn't metadata. That's important. It's just some additional information. So this gives you a true representation of the underlying data type as how Spark sees it, followed by the internal representation inside of Parquet. And then finally, the real useful or important part is this section here. So here you can see that given that I've already got, you may remember we had 985 rows here. So what Parquet has done is it's broken it down, and it identified that the entire set of data could be fit into one row group here. And we'll talk about that in a bit more detail. Here you can see these are the same columns of information, but here you can see, in addition to the type of information, you can see additional details as to like what compression algorithm was used. In this particular case, we've used gzip here. We can find additional pieces of information such as what type of encoding was used and various other pieces of information. And I would encourage you to take a look at the Apache Parquet homepage, and that gives you a lot more details and the various options, again, in terms of the types, the data types, as well as the different types of encoding and details like the possible types of compression encoding that can be used across various columns. Before we move away from this command, just worthwhile highlighting this piece of information here. This is quite handy because when we are talking about Parquet, obviously we had the benefit of compression. So what you're seeing here is a representation of the compression. So what it's saying is the original information was of this particular size, and post compression brought it down to this size here, and obviously was the compression ratio. Again, this is not necessarily a real world example. This has been mocked up using some sample data, and it's not really that big a data set. So you can see that in most cases compression isn't that good. But in the real world scenario, you'll find, again, it depends on the data types that you're exposing. If it's a fairly denormalized data set involving, again, depending on the cardinality of the data, if you have things that occur very, very frequently, you'll find again that the compression is extremely high. And that's it about this command. The last command we'll take a look at is we'll run the same thing again, and this time let's actually get a dump of that data and run it through less again. So here you can find much of the same piece of information as the previous command. So let's skip the first section and this section here. But you may remember in our previous discussion around concepts, we discussed the fact that the underlying file itself is stored in row groups, and within row groups you have these column chunks and this idea of a page that's breaking down that data into pages and sections. So here you can see that each individual data set, we can see how it's broken down into different pages. So again, since my data set's fairly small, it's only got one row group. So effectively, if we had a very large data set, so in my case, it's only about less than 1,000 rows and a relatively small data set. So collectively, Parquet, again, depending on the block size, it's identified that the number of row groups that it has to use. And in context of this particular demo, because it's a small data set, it's only got one row group. And you can see that these are all the unique values, or all the values, if you will. That's 958 rows of data. So if I scroll, and that's quite a long scroll, but you can see that these are all the different values for that first column, which is the street. And just at the end, yeah, just there. So then we can see that's the next column. So again, all these columns are stored together, and that's the whole magic of columnar store. It stores all of the columns adjacent so that it's much faster and allows for scan-based queries. And then you can see that's the next column. And again, obviously, it's got the same number of rows, and it's fitting inside of one row group. And here's the second column, and on till the last column. So that's about it for this demo. And in summary, we have seen how Parquet file some of the internals around Parquet files, and how it uses the various capabilities of compression and encoding and structuring of the data to allow for fast lookups and for fast analytical access. Let me take a step back and correct myself. It's really about how Parquet uses efficient storage, columnar storage, to allow for quick analytical queries. Again, have a look at the Parquet, the official document in this URL, and play around with the Parquet tools. I found that it's really handy to have Parquet tools when you're working with Parquet files, which you might not be the creator of those files, and you need to gain some quick insights into the files. So the Parquet tool has been particularly useful in helping discover the internal structure of the corresponding Parquet files. Hope you found this video helpful. Thanks everyone for watching.